Hello, welcome to Laws of Radioactive Decay, in which we'll do the first real new stuff in atomic physics in terms of radioactivity for you. Previously it's all been pretty much recapping what we did in physical science. Well, let's do the new stuff. The activity law, you'll find that on your information sheet. Looks like this. Now effectively we really only use this bit here. And this bit here never actually been used in a test or an exam. It's the derivatives. Basically it's still on the information sheet because some people didn't want to let go of it, some teachers, but it's a bit unfair to have it on when some students aren't doing derivatives in their maths classes, or differentials, sorry. And it's been years since I bothered using it, so pretty much ignore it. What we're interested in this bit here, and so what we've got is a couple new things. We've got the disintegration constant. Now every isotope has its own unique disintegration constant, and you either will be given it or you'll have to work it out in the question, and we'll go through that shortly. We have capital N stands for the number of atoms, and A is the activity. Notice there's no units for this because the number of atoms is pretty straightforward, but the activity can have a variety of units, as can the disintegration constant. There's no standard units, but it's dependent on what units you put in or what numbers you put in as to what units you get out, which is a little bit confusing for students who are used to having standard units. Let's have a look at some questions and we'll walk you through some typical things that you'll need to know. The disintegration constant for radium-226 is 4.3 times by 10 to the minus 4 per year. Okay, in this case the decay constant's per year. Calculate the number of atoms in the sample of radium-226 that has an activity of 3 kilobecquerels. Remember, becquerels is counts per second. So we have a disparity here between the activity, which is in per second, and the decay constant, which is per year. And so we'll have to fix that, and that's something we have to look out for in the question. So because it's given per year, we have to convert it, and we convert the decay constant from being per year to seconds by dividing it by the number of seconds in a year. And we get this. Now, this decay constant, 1.36 times by 10 to the minus 11 per second, is equivalent to this one, but we have to just be careful how we use it. When I said that every isotope has its own unique decay constant, these numbers are the same decay constant, just expressed in different units. Now once we get that into seconds, we can then put it into our rearranged formula, where we've got the activity is 3 kilobecquerels. Now we could have worked out how much activity that represents in a year by multiplying by this value. So there's two ways around it, but we should come up with the same answer. And this would be the number of atoms it represents. Because we're working on the assumption, and if we went back one, well, it's not an assumption, but we're saying that if you have a sample of an isotope, the activity is proportional to the number of atoms that you have and the decay constant. Now, if the isotope we're talking about has a very short half-life, this decay constant will be very large because you'll have a very high activity. If the half-life is very long, this decay constant will be a small value and the activity will be correspondingly small, and the activity will be proportional to how many atoms there are. If you have a lot of atoms, you have more activity. If you have only a few atoms, you only have a small amount of activity. So I hope that makes sense. So we've done that example, and we're also given this one, which is called the exponential decay law, where we have the number of parent nuclei at start. That's NO, whereas N is the number of atoms at the end of the time period, and we're talking about number of parent nuclei. I should have written there. Okay. Then we have equals e to the power of minus the decay constant t equals AO. Now AO is the activity at the start of the period that we're interested in, and A is the activity at the end of the period. Now that's equal to the count rate divided by the original count rate. Just put it into words. Now note that because in this equation here we've got e to the power of minus the decay constant t, this e is something some of you haven't probably used before, and so we need to be able to, instead of, some of you have only been raising things to the power of 10, or 10 to the power, but we've now got e being used, and depending on what maths you use, you're either very familiar with using e and how to rearrange it to get rid of e, or you're not. And so if we're working on this equation and we after something here, how do we get rid of the e? And the way to do it is to take the natural log. Now here we've got the natural log of the number of atoms, but it could also be the natural log of the activity ratio, where you have the original activity and the current activity, and that brings the decay constant and the time down to the same level mathematically, so we can solve it. Okay, now the natural log is of course on your calculator. Just make sure you're using the natural log rather than log which is to the base 10. Now if we bring this in, we are also given this equation here on your information sheet. So we're actually given quite a lot, and we're given the one that the decay constant is equal to 0.693 divided by the half-life. Now this is because remember, the half-life is when this activity would be halved, or the number of atoms would be halved, and so if you took the natural log of 0.5, that's where that value comes from, the 0.693. Now be careful of the units. So whatever units you put in here, either into the decay constant or more commonly into the half-life, will be the units of the decay constant. So if you put in seconds, you get a decay constant per second. If you put in days or years, you get a decay constant per day or per year. So you have to be careful about what you're putting in. Let's do an example. The half-life of radon 226 is 1,620 years. Calculate its disintegration constant, sometimes referred to as its decay constant. Putting the numbers in, notice that we get the decay constant per year. Note also, now we also have this formula here, which is a whole jumble of letters, many of which you might have used in chemistry, but let's just be careful with how we use them. N is again the number of atoms present. M is the mass, and of course we're doing physics, the mass is in kilograms. M is the molar mass, which you just get by reading off the periodic table. It doesn't have any units per se that we need to worry about. This one here is the interesting one, Na. Now in physical science, Na is Avogadro's number, and in your chemistry, if you're doing chemistry, Na is Avogadro's number, but in physics it's the kilogram mole, and so the units here are different. Look, warning. And a lot of students, when they come to use this formula, have fallen for the trap of using the wrong power here because they just want to use the chemistry or the physical science one. Make sure that you're using the kilogram mole. It's on your information sheet, and there's no excuse for using the wrong one other than you forget. Be careful. And there'll probably be an animation on the OneNote. Now you're able to do, oh, they got too small to read. Now they're big enough. You should be able to do all these questions and get your head around how to use those formulas. Now there's also some other questions, including these two, which you really need to do because they're slightly different ones. They look a little bit similar and work out the decay constant, but then you've actually got to work out how many atoms are present, so using those formulas we've just talked about. And this one here is you're actually given the relative atomic mass, and so it's good practice at using that formula as well. So have a go at those, and if you can do all those, you should be pretty much okay. And in the next video, we'll look at transmutations by nuclear reaction. See ya!